So the atom itself has no charge. But we are going to deal with a lot of atoms in this class going forward that have a charge. And an atom that has a charge is called an ion. When you eat sodium chloride or salt, it is not in the form of a neutral sodium atom and a neutral chlorine atom. It's in what we call ions. So they're charged atoms. A sodium ion has a +1 charge. And that is how we write the charges on our atoms. We write the symbol of the element in a superscript. We write a plus or a minus. If we have something that has +2 charge, we'll see later calcium gets a +2 charge, you would write it like that. Oxygen gets a 2-. So it would look like that. Okay. And you'll see plenty of examples of that. The fact that it has a +1 charge means that the protons and electrons are out of balance. If they're in balance, they completely cancel each other out, and the charge is 0. What do you remember about the number of protons for an element? Can it change? No. If the number of protons changes, the element changes. The number of protons is what determines what element it is. So, if we start balanced, and then all of a sudden we're unbalanced, but we're the same element, what does that say? What changed, the protons or the electrons?
Electrons.
The electrons had to have changed. And if we have a +1 charge, did we gain an electron or did we lose an electron? We lost an electron. So imagine we have an atom that has 3 protons and 3 electrons. They're balanced, right? There's 3 of each. If we lose an electron, all of a sudden these cancel, and there's a +1 left. If we gained an electron, then those cancel and there's a negative left. If we had gained 2 electrons, we'd have a 2- charge, or a -2 charge. So the fact that we have a positive charge means that we lost electrons. And moving forward, everything's going to gain or lose electrons. Remember, the protons don't change. So how many protons does a sodium ion have? Sodium is right there.
Should have 11?
It has 11, right. The atomic number of sodium is 11. So a sodium atom or ion, doesn't matter, has 11 protons. How many electrons does this sodium ion have? 10. It started with 11 and then lost 1. So now it has 10. There are 2 types of ions. There are cations. Cations have positive charges, whether it be +1 or +2 or +3, or you can even be +4. That means they have fewer electrons than protons. That means they lost electrons. If you have fewer electrons, that means you lost electrons because you can't gain protons. The opposite of cations are anions. Anions have negative charges. Anions gained electrons. That might help you. If it helps you, use it. If it doesn't help you, forget it.
There's another trick to know which one are positive and negative. For anions, you can say the AN for A negative, and then for the cations, you could say the T is like for the positive. So it's a different way.
Whatever works. That's just as valid, if probably more valid than this. Okay? Whatever works for you. And there's gonna be a lot of examples of things like this. Usually I'll tell you how I remember them. This one I don't have a specific way to remember, I just remember it, so there's two things. But going forward, I'll tell you how I remember things, and you can remember them however you want. So this is how we make a magnesium cation. Magnesium is there, and it likes to lose 2 electrons. When it loses 2 electrons, we get an Mg2+ cation. So this is a neutral magnesium atom. If you added everything up in here, there's going to be the same number of protons as there are, same number of protons. In this case, there are 12 neutrons also. But in the atom, neutral atom, there are 12 electrons. Magnesium is here, it's number 12, so there are 12 protons. If it's neutral, there has to be 12 electrons also. Over here, we formed magnesium cation. We still have 12 protons and neutrons, that never changes. But we now have 10 electrons. And so the positives and the negatives are out of balance. There are 2 more positives than there are negatives. So we have a 2 positive charge. Nitrogen likes to gain electrons. And nitrogen likes to gain 3. We'll see why some gain 1, 2, and 3 later on. But for now, nitrogen gains 3. So nitrogen starts with 7 protons. It is number 7. And it starts with 7 electrons, because it starts balanced. But it likes to gain 3. So now there are 10 electrons, but there are still only 7 positive protons in the nucleus. And so we have a -3 charge, because there are 3 more electrons than protons. So, how many protons did we say a sodium atom had? 11. How many electrons does this sodium ion have? 10. 11 minus 1 is 10. So here's chloride ion. Chlorine is there. How many protons does it have?
17.
17. It's number 17, so it has 17 protons. How many electrons does this chloride ion have?
18.
18. It started with 17 as a negative charge, -1 charge. So that means it gained 1 electron. If you start at 17 and you gain 1, you're at 18. So it has 18 electrons.
So whenever there's a negative sign next to the element, you can see it as, so in this case, the chloride, which is negative, it gained an electron, so electrons are negative, so it gained.
Right. And that tells you how many it gains. Because it's meant there's assumed 1 here, it's telling you it gained 1. If it was 2 minus, that tells you it gained 2. If it was 2 plus, that tells you it lost. What about this oxide ion? How many protons does it have? 8. Oxygen is 8, so it has 8 protons. How many electrons does it have?
10.
10. 8 plus 2 is 10. There's an aluminum ion. Aluminum is there. 13 protons. How many electrons?
10.
10. 13 minus 3 is 10. So here we're going to go the opposite direction. You have the number of protons and the electrons, and we're going to write the symbol for it up here. So, one ion has 20 protons and 18 electrons. First thing I would do is I would just figure out what element we're talking about. What element has 20 protons? Calcium. Calcium has 20 protons. The number of electrons is going to tell us our charge. What's the charge on this calcium?
Plus 2.
2 plus, okay?
Is it the same thing, or it has to be 2 plus? Like if you put positive 2 instead of 2 positive, is it the same thing?
The convention is to put the number before. If you ever put 2 plus, or plus 2, something like that, I'm not gonna mark it wrong. I think a lot of, I always write it that way, the right way, but a lot of times I say it incorrectly. I'll say plus 2. So that is number 1. Number 2, what element has 16 protons?
Sulfur.
Sulfur, what's the charge?
2 minus.
2 minus. It has 2 more electrons than protons. Number 3, what has 26 protons? Iron. What's the charge?
3 plus.
3 plus. It lost 3 electrons, so it has a positive 3 plus charge. Does this make sense? This isn't too hard, right? It's just counting. I think counting is a prereq to this class. Okay. There are a lot of things up on this periodic table other than the symbol and the name, right? So we just learned what the numbers tell us. These numbers up in the corner, the ones that go up by 1. But there's also this number down here. And that number, the little number, the one with all decimal places, is our atomic mass. The atomic mass allows us to compare the mass of an atom of one element versus the mass of an atom of a different element. And when we're talking about atoms, the unit that we're going to use is called an atomic mass unit, or AMU. It doesn't have any real world application. Okay? There's no scale that you can put something on and it's going to weigh in AMUs. AMUs are only for comparison. If you have something that weighs 2 AMUs, it's twice as heavy as something that weighs 1 AMU. Okay? So you can compare that way. The way this was set up is they figured out how much a carbon atom weighed and said, well, carbon is number 6. It has 6 protons. Most carbon atoms have 6 neutrons also. So that's a total of 12, right? Let's say carbon weighs 12. And when you set that benchmark, everything comes from that. So a hydrogen has 1 proton, no neutrons. So it weighs 1. In the end, this is basically the mass number we talked about in the video. Add up the protons and the neutrons, and that is going to be your atomic mass. Okay? Now, we'll get to why up here we have these numbers that aren't rounded numbers. If you look at carbon, it doesn't say 12. If you look at hydrogen, it doesn't say 1. Talked about that. Okay. So the number down here is the relative atomic mass or average atomic mass. I said most carbon atoms have 6 neutrons. 6 protons plus 6 neutrons equals 12. But some of them have 7 neutrons. Some of them have 8 neutrons. And so what's up here on the periodic table is the average mass of all of the carbon atoms in the universe. So the fact that this number up here is 12.011, it's very, very, very close to 12. That tells us that pretty much every carbon atom in the universe is 12. There are very, very few of them that are not 12. Take up all of the isotopes of carbon, and we'll assume that there's carbon 12, carbon 13, and carbon 14. 3 different isotopes of carbon. And you take the average mass of every single carbon atom in the universe, add them all up, divide by the number, you would get 12.011. But there's a much easier way to calculate that number than just adding up and dividing. Silver has an average atomic mass of 107.9. This tells us that there are 2 isotopes of silver, 107 and 109, just based on that number being the average. Can you tell me whether there are more silver atoms that have a mass of 107 or a mass of 109? Why 107?
It's closer to 107.
Right. The average is closer to 107. That means there must be more of them that are 107 to 109. So if we put, imagine a number line. You have 107 and 109. We have this line across, and somewhere on this line, we're going to put a mark where the average is. If we have 3 107s and 3 109s, the average is going to be right in the middle. But if we get rid of a 109, now the 107s win. So think of it as a tug of war. Now there's 3 107s and 2 109s. The average is going to be closer to 107. So just by looking at that, we can tell that there are more 107s than there are 109s. And we can calculate these numbers. Like I said, we don't have to add up and divide. That equation looks nasty, okay? Doesn't look necessarily look hard, there's just a lot of crap in that equation. This is easier than that makes it look. Basically what we're going to do is we're going to take the mass of each isotope and multiply it by the percentage of the total population of that element that isotope makes up. So if isotope 1 makes up 30% of all of that element in the universe, we're going to take that mass, multiply it by 30%. If isotope 2 makes up 70%, we'll take the mass of isotope 2 and multiply it by 70%. Add the two together, and we have a relative or average atomic mass. So this is an example of how you would, a question where you would calculate that. So we've discovered a new element. Okay? We found the 2 isotopes. We know their masses. And we know the percent abundance. The percent abundance is what we call the percentage of how much of that element is made up of that isotope. So this is telling us that there are 2 isotopes of this element. The isotope with a mass number of 22 makes up 75% of that element. And the other 25% is made up of the isotope with a mass number of 20. So in order to get our average, all we do is we take our mass of isotope 1, we'll call this one isotope 1, and the mass is given to us at 21.995 when multiplied by the percentage, 75%. Now you don't put 75% into your calculator. If you wanted to multiply something by 75%, what would you type into your calculator?
0.75.
0.75. You need to take a percent and divide by 100. If you remember the equation for calculating percent, at the end you always multiply by 100. So you need to divide by 100 to get it back into decimal form. So it'd be 0.75. So we're gonna take 21.995 times 0.75. And then we'll do the same exact thing for the other isotope. We have 19.996 times 0.25. Someone help me out and multiply those two numbers.
16.49625.
Okay? And then multiply these two numbers.
4.999.
4.999. And now all you have to do is add these together. Is that right?
21.9615.
Yeah, no, you're right. 21.96. That?
I got a different answer now. 21.49525.
That's the one I got.
49525.
I think that's what
I think that's what he originally thought.
So that is our average or relative atomic mass. If we were going to put our new element on the periodic table, that would be the number that we put on there. If we had to round the sig figs, how many sig figs would we have?
5.
3.
Very.
You still with 5?
Yes.
Right.
I think
Oh,
5.
Isn't it
Is
5?
that zero?
Isn't it 5?
Smallest number that went into it.
It should be 21.495.
Where's the 2 coming from?
Yeah.
The percentage?
I got lazy. 75% was 75.00, so it should have been 0.7500.
Oh,
So 4. You're probably going to do the same lazy stuff that I just did. So what I do is I do the math. I do it however I want to do it, okay? And then I go back to the question itself to figure out the number of sig figs. Because these didn't really have, that one didn't have the right number of sig figs either, right? I wait till the very end and I figure out how many sig figs I need from the question itself and then round the answer, yeah.
I have a question. But for these, when you first step, that's multiply. But the last step is add up, so you should keep the last step sig fig. Is that correct? So which means you have to keep after decimal only 3 number there. So it should be 21.495. Need to see the last step, is that
Yeah.
correct?
Yeah, you're right. So what she's saying is that we did multiplication, then we did multiplication, but then we added. And with adding sig figs, you would draw a line. Yeah. You won't be graded on sig figs on these. Okay, I don't think you ever even get one where you have to write out a number like that. Would be my guess. You have a question?
Yeah, quick question. So when you said you need to go back to the original problem to see exactly how many sig figs are at the end of your problem, how come we went to the percentage rather than the actual mass to look for the original amount of sig figs?
You're looking for the smallest number that went in. So we looked at these 4 numbers. And these 2 each have 4, these 2 each have 5. So we said it's 4.
So it's always the least
Right.
number that we chose.
Yeah.
Okay.
Is this hard? Take the mass, multiply it by the percentage, do it for each isotope, add them up. Okay? The most likely way that you'll run into this problem is you'll be given information like this, imagine this column didn't exist, you would calculate an average, and that average will be an actual element, and the question will be asking you which element is this. And so in that case, significant figures would be irrelevant because your answer is element, not number. So if we look at the periodic table, the numbers go 1, 2, 3, 4, 5, 6. And that obviously made sense to you weeks ago because you count up the 1, 2, 3, 4, 5, 6. But now we know that it's counting 1, 2, 3, 4, 5, 6 because that's the increasing number of protons, right? When you do that, you don't just create one big long string, right? It's not, the periodic table is not one big long line of elements to string around the room. There are definite rows and columns, and those are there for a reason. The columns are called groups. Sometimes they're called families. I don't think you'll ever hear them called families again in this class. They're called groups, okay? A column is called a group. First column is called group 1. There's a Roman numeral 1. That's group 2. And then you'll usually see 3, 4, 5, 6, and so on. Okay? Rows are called periods. That's why it's the periodic table of elements. This is period 1, period 2, period 3, and so on. There are numbers, good old-fashioned Arabic numerals right on the side, right? Periods tell us a lot, okay? And the reason that things are grouped as they are in the periodic table is because as you go from left to right in the periodic table, there are certain trends that happen over and over and over again, no matter which period you're in. These are properties that we say are periodic, meaning they happen again and again. That's why it's a periodic chart or periodic table. So this is the same periodic table that you've seen before. Yeah.
Why for 8 through 10 does it have like the one more thing over it? Oh no.
Like segment.
Yeah.
That?
Yeah.
Five, six, 7, 8. To be honest, I never use the Greek ones. I just use the numbers.
Okay.
There are 18 columns, 1 through 18. I honestly, I don't know why it goes 7, 8, 8, 8, 1B, 2B. Because you have these periodic trends, as you go from left to right, you get the same things happening, the same changes. That means the periods, when you stack them on top of each other, the things that end up on top of each other, the elements that end up in columns, have the same properties. And so things in a group, elements in group 1, have pretty much the same properties. Hydrogen is going to have pretty much the same properties as potassium and francium. Over here, oxygen is going to have pretty much the same properties as selenium and polonium. If it's in a group, it's going to behave very, very similarly. This is potassium in water. It reacts violently. I think in lab a week or two ago, you had to put an example of a chemical property of sodium. And what most people put was that sodium reacts violently with water. Sodium is here, potassium is there. It reacts violently with water. So does lithium. so does rubidium, so does cesium, and so does, if you're in that first group, you react very violently with water. What actually happens here is it reacts with the water, it produces hydrogen gas. At the same time, it puts off a whole lot of heat. And what did we learn about hydrogen gas in heat? Remember the balloon?
It's
Very flammable.
It's very flammable. So if you're making hydrogen gas and a bunch of heat in sparks and stuff, you get a big boom. Yeah. These are group 1. Group 1 metals are called alkali metals. That's a name you need to know. There are a few groups that have common names and you need to know them. Group 1 is the first of them. If it's in the first group, the first column, it is an alkali metal. We already talked about the stair step, right? The metalloids are on the stair step. What are to the right of the stair step? Non-metals. So we have metals, metalloids, and non-metals. The metalloids look like a metal, but behave like non-metals. So I think in one of your test tubes last Thursday you had silica. Remember that? You remember what it looked like?
Yellow.
Sulfur.
Oh, grayish.
Silicon is gray. It's silver. It's shiny. We said metals are shiny. But silicon doesn't conduct electricity. And the two things we said you had to have to be a metal, you had to be shiny, you have to conduct electricity. So silicon has a physical property, what it looks like a metal, but it behaves chemically like a non-metal.
Can I ask a quick question?
Yeah.
If the characteristic of a metal as its physical appearance resembles a metal, but its chemical properties doesn't resemble a metal, then why isn't it classified as a non-metal if its chemical properties are non-metal?
Because a non-metal would not be shiny either. So metals are shiny and conductive. Non-metals are not shiny and not conductive. Metalloids are shiny but not conductive. And as far as I know, there isn't anything that's conductive but not shiny. So this is silica. That and these other metalloids definitely look a lot more like these metals than the non-metals, right? That's probably easy to see. But if you tested them, they would not conduct electricity. So now we've got groups, we've got periods, we've got metals, non-metals, and metalloids. And there's a few more classifications we're going to talk about. There's the main group elements. Main group elements are 1 and 2, and then these over here. Transition metals are the ones in between them, in this little cut-in thing here with an empty spot here. And then there's also intertransition metals. Don't worry about these. You want to just cross intertransition metals right off that. So you've got main group elements and transition metals. Those are the two you need. So we said group 1 are alkali metals. You're going to kill me when I tell you number 2, but it's not my fault. Group 2 are alkaline earth metals. That's a very similar name. It doesn't make any sense to me either, but the way I remember it is for some reason, calcium seems earthy to me. When I think of calcium, I think of earth. Calcium is in group 2. So group 2 must be alkaline earth metals. Okay? Believe it or not, that's how I do it. If you send me an email tonight asking me whether strontium is an alkaline metal or an alkaline earth metal, I'm going to look, is it in the column with calcium? Calcium reminds me of earth, So these must be alkaline earth metals. Do what you need to do to remember them, okay? If you want to remember it, alkali has one word, that's group 1. Alkaline earth is 2 words, that's group 2. That works too. Whatever works for you. We then skip all this stuff in the middle with names and we go all the way to the other end. Group 17, fluorine, chlorine, bromine, iodine, astatine, we call halogens. These are nonmetals and they're diatomic. The diatomic molecule is an element that doesn't like to exist in single atoms. So you will never have a neutral chlorine atom floating around as itself. So that's chlorine. You will never see that. It always exists in pairs. So it's Cl2. That's saying there are 2 chlorines. Same thing with fluorine. It's always F2. Or bromine is Br2. That's a diatomic element. And I believe that's on another slide, but just in case it's not, there are a few other elements that are also diatomic. You have group 17, and then oxygen and nitrogen and hydrogen. So the way to remember it is you have this L shape here. You have that group, oxygen and nitrogen, and then hydrogen is just kind of an outlier. So remember the L plus hydrogen. All the way on the end is group 18. They're the noble gases. They don't react at all. Not at all. So pretty much, other than them being examples of something that don't react, we'll never see them again in the semester. Sometimes they'll pop up here and there, but they're not going to do anything. They're called noble gases because it reminded someone of a stuck-up nobility person. They don't interact with the common elements, right? So they're the ones walking around using their forceps and going on their business, not dealing with anybody else. So these are the noble gases. These are these are the diatomic elements that we just talked about. Remember in the lab on Thursday, we all were having this debate about whether hydrogen is a metal or a non-metal, right? And I said in some periodic tables, hydrogen is located in 2 different places. It's obviously here. Where is the other one? Next to helium. So if it's in next to helium, it's in the halogen group 17 group. It's in that column. And if it's in that column, it's diatomic. So if that helps you remember the hydrogen is the outlier over here is diatomic, that's great. But these are the ones that you need to know. You will be asked multiple times, which elements are diatomic? Multiple times when we get into chemical reactions. And let's say you make chlorine gas in a reaction. You're going to need to know that chlorine is diatomic. Because if you don't write that and you just write Cl, it's going to be wrong. Chlorine by itself is always diatomic. So we were going through different elements before. And we were saying, if this element forms an ion with this charge, how many electrons does it have? And what does that mean in terms of how many electrons it gained or lost? And you might have seen a pattern. We did several different elements and they all seem to have the same number of electrons also. So, we said sodium, which is here, forms a +1 or 1 positive charge. Every single group 1 element, every alkali metal forms a 1 plus charge. All the time. Never anything else. The alkaline earth metals in group 2 always, always, always form 2 plus charges. Oxygen, sulfur, the things below it form 2 negative charges, and halogens form -1 charges. Always. And the noble gases do nothing. Do you see a pattern? What is the pattern that you see?
They gain electrons and
Gain and then, which one's gain? And so 17 is here. Which other one's gain? Not just 17, but also 18 is noble gases.
Oxygen is
The one that oxygen is in. So 16. 16 and 17 gain. 1 and 2 lose electrons.
Further to the right. Yeah.
16 and 17 are on the right, they gain electrons. Things on the right are going to gain electrons. Non-metals gain electrons. If you're on the left, if you're a metal, you're going to lose electrons. Oh, okay. I couldn't remember the what I was going for here. So this is a heavy metal cat. Okay? Metals form cations. Okay? If that helps you, great. If it doesn't, block it out. Okay?
Oh, I can think of something like cat.
Oh, crap.
The guitar.
Okay. Noble gases are the most stable. That's why they don't react, because they're very stable. And we say they have 8 valence electrons. Valence electrons, we'll talk about exactly what a valence electron is later, they're on the outside. So if you imagine an atom, you have the nucleus in the middle, and the electrons flying around an electron cloud around it. The only electrons that can react are the ones that are on the very, very outside of that cloud. And every atom wants to have 8 valence electrons. And they're going to react to get 8. If they have 7, they're going to react to gain 1 to get 8. And actually, you can drop backwards. Metals will have too many, and so they'll get rid of a couple to fall back to 8. When atoms form ions, they're doing it in order to become like noble gases. They want to become noble gases in terms of the number of electrons. So this says they want to become the nearest noble gas. So if I'm looking at fluorine here, what is the nearest noble gas? Neon. If I'm looking at oxygen, what's the nearest noble gas? Neon. If I'm looking at sodium, what's the nearest noble gas, keeping in mind you can go both forwards and backwards on the periodic table? Neon. You can go backwards from 11 to 10. It's just one step away from neon, right? In our table, in terms of just space and distance, sodium is a lot further away from neon than fluorine is. But in terms of electrons, they're equally distant. This one has 1 fewer electron than neon. This one has 1 more electron than neon. So metals are going to fall backwards to a noble gas, and the nonmetals are going to go forwards to a noble gas. The metals, in order to go backwards, they're going to lose electrons. Nonmetals over here, in order to go forwards to the right, they're going to gain electrons. So how many electrons does a sodium atom have?
Oh, electrons?
How many electrons does sodium ion have?
So,
10,
10. What about magnesium ion?
10,
10. It has 12 to start, but it lost 2, so now it has 10. What about aluminum?
10,
10. These here, in this group, are going to lose 3 to go backwards. So aluminum is going to lose 1, 2, 3 to get back to neon. How many does oxygen ion have?
10,
10. Starts with 8, it's going to gain 2 to get to neon. Fluorine has how many? The
10.
fluoride ion has 10. 9. Gaining 1 to go to 10. And how many does a neon have?
10,
10. So everything on either side of neon gains or loses electron to get to neon. Whether that means gaining to go forward to neon or losing to go backwards to neon. So if we're going to look at beryllium, beryllium is right here. What charge do you think a beryllium ion is going to have? 2 plus. We said everything in this group has a 2 plus charge. So if we're going to write the symbol, the beryllium ion is just going to be beryllium 2 plus. What about aluminum? What's the symbol for aluminum ion?
yeah.
There you go. Al, 3. Is it plus or minus?
plus,
It's plus. Aluminum is to the left of the stair step. So it's a metal. It's closer. If aluminum goes backwards, it can go 1, 2, 3 to get to neon. If it has to go forward, it has to go 1, 2, 3, 4, 5. So it's going to go to the closest one. It's closer for it to go backwards, so it's going to form a 3 plus charge. What about phosphorus? It's 3 minus. So we got phosphorus, 3 minus. Everything in this group will go to the right. It'll gain 3. It'll gain 1, 2, 3. Phosphorus is closer to argon than it is to go backwards in neon. Okay. So we just talked about valence electrons. We said valence electrons are on the outside of this cloud. In order to really talk about what valence electrons are, what they really are, we need to have a better picture of what the outside of a cloud looks like. And there are 2 ways that we're going to visualize electrons going around the nucleus. There's the old way and the new way. The old way is a lot easier than the new way, and in a lot of cases, it actually is the better way to think about it. Okay? In terms of valence electrons, this is going to be the way that you're going to want to picture this. It's like a solar system. The nucleus is the sun in the middle, and then you have these orbits going around. And they just build out basically in shells going around. And so that valence electrons are going to be how many electrons are in the outermost shell. So if you have an atom that only has 1, 2, 3, and 4, 5 and 6 have nothing in them, number of valence electrons are going to be how many are in 4. If you have this one, it's going to be how many are in 6. The electrons in 1, 2, 3, 4, and 5 are protected. They're inside, they can't do anything. The only things that can react are the electrons that are in the outermost shell. This is good for conceptualization, for visualizing things in your head. But unfortunately, it's not how things actually work. It's not this neat little planetary system. It actually is a cloud. And so we can use this for something. And coming up slides, we're going to have to think of it as clouds. This is the modern model of an atom. These are electron clouds. Their electrons are flying around randomly. They're not just in circular patterns. And so what you get is a mathematical model that predicts where an electron should be, but it's never going to tell you where it is. And that's not something we're going to have to predict in this class. That's an entirely different class. In the modern model, instead of orbits, circular orbits, we have orbitals. And an orbital is three-dimensional. It's not that orbit, circular orbit that you can draw on a blackboard. It's three-dimensional. And we talk about principal energy levels. It's the same idea as which shell you're in. As you go out, it increases. You have 1, 2, 3, and 4. But here they're called principal energy levels. And the principal energy level is just going to be the period number. That's how you're going to know what principal energy level you are in. If you're dealing with two different atoms and they have the same principal energy level, meaning they're in the same period or row, the orbital, the cloud of electrons, is going to be roughly the same size. As you go down, as the principal energy level increases, your cloud gets bigger. And it makes sense. You know now that elements down here have a whole lot more electrons than the ones up here, right? Hydrogen just has 1 electron. If you have more electrons, surely your electron cloud is going to be bigger. So your cloud is going to get bigger and bigger. There are 4 types of orbits. Okay? These are shapes. Do not worry about these shapes. If you're someone that is good at visualizing shapes like this might help you. Okay? If you are not, do not worry about these shapes. We have s orbitals, p, d, and f. You will need to know those letters, but they're going to become very clear in the next few slides. What I want you to really look at here is, you see how this is just one sphere, right? And then this has 2 parts. And this has 4 parts, and that has 8 parts. If each part can hold 2 electrons, how many electrons can that hold? 2. If each part can hold 2 electrons, how many can a p orbital hold? 4. How about a d?
8.
8. An f? 16. Okay? So as you go from s to p to d to f, they're going to hold more electrons. And there's going to be a whole lot easier way to figure out how much each one holds than this. Your periodic table is going to tell you. That's another thing that it tells us. Okay? What you want to be able to do is, when you see that periodic table, you need to be able to imagine these letters imprinted on that periodic table. These are the S's. The first 2 columns are S's. transition metals, the ones in the middle here, are D's. This block over here are the P's. And B's down here are the F's, although you will never do anything with an F in this class. Not even your grade, hopefully. Okay? When you get down to these F's, it turns into these massive problems. And that's not something I would ever give you. So you need to know that an F orbital exists, but you won't have to do anything with the F in this class. But you're going to use S, D, and P over and over and over again. So you need to remember S, D, and P. So, how many columns are in the S group? There are 2 columns in the S group. If we go back, how many did we say S could hold? 2. How many did we say a P could hold? Never mind. Never mind. I'm not a spatial person, okay? These things don't mean a whole lot to me. There's actually another one that's drawn, that should be drawn here. And I guess for an artist it's understood. For me it's not, okay? There should be another one, so there should be 6 total. How many columns are in the P group? 6 columns. So if there are 6 columns in a P, how many electrons do you think a P holds? 6. How many columns are in the D group? 4, 5, 6,
10.
7, 8.
10.
I counted. 1, 2, 3, 4, 5, 6, 7, 8.
10.
Keep going.
That is a 10.
I can count. So there are 10 in the D. So how many elements, how many electrons do you think a D can hold?
10.
10. S's hold 2, P's hold 6, D's hold 10. For your knowledge, there are 14 down in the F, but don't worry about it. So, it's going to be helpful to you remember that S is 2, D is 10, P is 6, but if you forget, periodic table tells you there are 2 columns in S, 10 columns in D, 6 columns in the P.
So the pictures weren't helpful at all.
Yeah, that's exactly
Because
what
we
I was
said
gonna ask.
4 and
Yeah.
then
Yeah.
like 8 or whatever.
I'm trying to figure, because I don't know if they're it seems like they're purposely missing. I don't know.
I don't get that.
I guess I don't either.
Yeah.
That slide will be gone next semester.
Yeah.
If you want to retake it next semester, so you can, guess.
It'll have another.
Cross the pictures out or something, okay?
The helium is a.
So if you look up here, someone has actually drawn helium
Oh, so this is just old.
here. It's not old. Hydrogen can also be drawn here, and helium can also be drawn here. When we start to fill these orbitals, we're going to start to fill these orbitals, put electrons into them, it'll be cleared by helium in an S. Okay? It'll be very clear when we get there. So this is what I mean by we're going to start filling orbitals. And there are a few different ways that we're going to write this out. This is the first one. This is called an orbital diagram. Orbital diagrams have boxes and arrows. That's not good. They have boxes and arrows. Okay? If I ask you on a quiz to draw me the orbital diagram, I'm most likely going to tell you an orbital diagram is the one with the boxes. If you see it on the final exam, they are not going to be that nice. So you need to know that the orbital diagram is the one with the boxes. Okay? So what we're going to do is we're going to represent electrons with arrows and orbitals with boxes. Every box holds 2 arrows, that's 2 electrons. So, how many electrons go in an s orbital?
2.
2. So an s gets 1 box. How many electrons did we say go in a p?
6.
6,
6. So how many pairs are in 6?
3,
3. So a p gets 3 boxes. How many electrons did we say are in a d?
10.
There's 10. So how many boxes do you think a d is going to get?
5.
5. Always. No exceptions. Even if some of them are empty. So you see here, you don't know why the electrons are where they are yet, but that box is empty. There are no electrons in that box, but because it's part of a P, you have to draw the empty box. So this is carbon. If you look at a carbon atom, how many electrons does a carbon atom have?
6,
6. For a neutral atom, the number of electrons are going to be the number here. Carbon is 6. So carbon has 6 electrons. And what we're going to do is we're going to start in the top left corner of the periodic table and just read left to right, top to bottom, until we get to carbon. And we're going to fill orbitals as we go. So the first orbital we hit is the one that hydrogen is in. Is that an S, a D, or a P?
S,
That's an S. And it is in period 1, so it is 1s. Ignoring electrons so, to this point, we're going to move on. We've completed this first row, right? So we went left to right. We've got 2 in our S. That's 1, 2. Then we go to number 2, period 2. In the first orbital that we hit, right here, is that an S, a D, or a P?
S,
That's an S. It's in period 2, so it is 2s. We put a box, but we're not the carbon yet. So we've got 2 here, or 2 S's, then there's a big gap here. We jump all the way across, and then what orbital is this?
P,
It's P. What number?
2,
2. Well, it holds 6, but it's in period 2, so it is 2p, and p gets 3 boxes. So now we have our boxes drawn. Somebody have a question?
No, but
So we have our boxes drawn. Now we have to put our electrons into our boxes. We said carbon has 6 electrons, and there are rules about how we're going to put arrows in the boxes. We said s orbitals get 1 box, p gets 3, d gets 5. Every box is going to get 2. You can get up to 2, and you're going to write them as arrows. Okay? Don't worry about this exception yet, we'll get to it. There are rules about how you can put these electrons in. They have fancy names that we'll go over, but in reality, they're not that complicated. Okay? The first one is called the Aufbau principle. That just means you start with the lowest number. Start on the top left and go up, which is why we went 1s, 2s, 2p. You already did that. You know the Aufbau principle. The next one is the Pauli exclusion principle. This says that you can only have 2 electrons in each box, no more. And if you have 2 in that box, they need to be pointing in different directions. You cannot have 2 arrows in a box pointing in the same direction. Okay? Complicated physics, but basically what it says is you can't know where something is and what spin it has at the same time. Okay? That's well beyond this. You can't have 2 arrows pointing the same direction in a box. And so by convention, we put the first one up, and if you put the second one in the box, put it down. But we'll do plenty of examples. And the last one is Hund's rule. This says that electrons are antisocial. They don't want to be in a box with another electron if they don't have to. Which is why, when we got to P, carbon has 2 electrons in the P orbital. We're going to put one here and one here. We're not going to put the second one here. They don't want to be with each other. If we had a third one, it would go here. That would be nitrogen. Nitrogen would have one more electron, it would be an up arrow here. And then, if you want one more to oxygen, now you have to pair them. So you have a down arrow here. So the 3 rules you'll become very comfortable with. So we're going to do some examples. Do hydrogen first. So the first thing you do is just write the symbol for the element you're doing. So hydrogen is H. Hydrogen is in the top left corner. What is the first orbital that we have? Always.
1s.
1s. You can never do one of these orbital diagrams without a 1s, because even the first element has 1s. And so the 1s gets us through the first 2 elements, helium and hydrogen and helium. Because we're dealing with hydrogen, we're already done with our boxes, right? Because hydrogen is in that 1s. It's in 1s. How many electrons does a hydrogen atom have? 1. It is number 1. So it has 1. So I'm going to put an up arrow, and we're done. So you need 3 things. You need the symbol, you need to label the orbitals, and then you need to put the arrows in the boxes. Hydrogen is the simplest one there is. Let's do phosphorus. Symbol for phosphorus is P. When you start writing your boxes, start in the top left corner and just work your way to it. So the first one we always get to is 1s. Is phosphorus in 1s? No, we're not to phosphorus yet. So once we fail the 1s, what's the next orbital we come to?
2s.
We come to 2s. This was 1s, this is 2s. So I put 2s and I give it a box. S's get 1 box. Have we made it to phosphorus yet?
No.
No.
No. So we move on. What is this?
2p.
This is 2p. How many boxes does p get?
3.
3.
So I'm going to put 2p, and I'm going to draw 3 boxes. Are we to phosphorus yet?
No.
No. So we're going to move on. Come down to here. What is this?
3s.
3.
This is 3s. S's get 1 box. Have we made it to phosphorus yet?
No.
No. So we move on. Now we're over here. What is this?
3p.
This is 3p. And p's
3 boxes.
get 3 boxes. Have we made it to phosphorus yet?
Yes.
Yes. Now we've got our boxes drawn. We just have to put our electrons in. And so how many electrons does a phosphorus atom have?
15.
There's 15 of them. So we are going to start here and work our way up until we put 15 arrows in. First one's going to go here. We can't move the 2s until 1s is filled. So there's 1, 2. And then this is another s. So I go 3, 4. And then get to p. I want to go 5. Where does number 6 go?
The second box.
The second box. It's going to go like that. That's number 6. 4, 5, 6. And then that's number 7. But we can't go on to S until the P's are full, so now we have to pair them. We have 8, 9, 10. 11, 12, 13, where's 14?
The second box.
Where's 15?
The last box.
And that's 15. You said phosphorus had 15, so we're done. This is your orbital diagram for phosphorus. Here's cobalt. Okay. Now we're going to hit that exception. We're going to do cobalt. Where is cobalt? Can somebody find cobalt?
27.
4D.
27.
It is right there. It's 27. What orbital is this? What letter? What letter?
D.
It's D. The number is going to trick you up. Okay? The D's are one number behind.
Boxes or like really nine?
Number. And so, what number is on this S orbital? What number is on this P orbital? 4. It's in period 4. The D's are one number behind, so this is 3 D's. If it's in period 4, it's 3 D. Okay? Yes.
And so if it's in period 5, it would be 4D?
4D, yes. And the reason it's behind is because electrons like to go where it's easiest for them to go. And if you do all the math and everything, you figure out electrons would rather go into a 4s than a 3d, which is why the 4s comes before the 3d. If you want to understand the reasoning behind that, I'll be happy to explain it to you. If that's just more complicated to you, don't worry about it. Just remember that the D's are one number behind. Okay? So, how many electrons are in cobalt?
27.
27. So we're going to put cobalt. What's my first orbital?
1s,
1s. It's one box. Then what?
2s,
2s. One box. Then what?
2p,
2p
3
gets
boxes.
3 boxes. Now what?
3s,
3s. One box. Then what?
3p,
3p gets how many?
3 boxes.
3 boxes. Then what?
4s,
4s gets 1 box. Then what?
3d,
3d gets how many boxes?
5 boxes.
5 boxes. Okay. So now I need to put my arrows in until I hit 27. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Stop. So the way I see it, if you can do one that has a D in it, you can do the easy ones that don't have a D. So if you can do cobalt, you can do phosphorus and hydrogen, right? So if you focus on doing your practice problems here, or even here past the first D, if you can include a D, that's as hard as it's going to get. Because I'm not going to give you one that has these F's down here. So the box in the arrow one is the orbital diagram. But that's a lot of work. And it's hard to read off, right? You can write that out, you understand it, but it's hard to say arrow, arrow, 2s, arrow, arrow, 2p, such and such. And so we shorthand this into something called an electron configuration. It's going to be very, very similar, but instead of having boxes and arrows, we're just going to say how many arrows are in each one. So, how many arrows are in this 1s?
2,
So I'm going to put a superscript 2. How many are in this s?
2,
How many are in that p?
6,
6. How many?
2,
2,
6,
6,
2,
2,
7.
7. So if you just wrote this part up here, that would be the electron configuration. And that you can easily read out. You would read that 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. So this is carbon. 1s2, 2s2, 2p2.
So then a really easy way of determining the element would just be counting the superscripts, right?
Correct. You can add up the superscript. You can say there's 2, 4, 6. So there's 6 total. Carbon is 6. Okay. When you start to do these, you're going to find that you know what you're doing. You don't need to count arrows as you go. And you don't need to count electrons. If I say sulfur, what orbital is sulfur in? 3p. And how many electrons are going to be in that 3p? 4. So you know that sulfur is going to have 3p4, and everything below that's going to be full. So if you know that everything here is full, and you know that S's have 2, P's have 6, you can just go 1s2, 2s2, 2p6, 3s2, and then you stop and think. Sulfur has 4 in this, so then it's 3p4. Okay? But there is no harm whatsoever in going back to the beginning and counting the arrows as you put them in. It's just you may find there's quicker ways to do it. If you figure where you end, you know how you had to have gotten there. So here's phosphorus. Somebody read off to me the electron configuration for phosphorus. 1s2, 2p6, 3s2, 3p3. 1s2, 2s2, 2p6, 3s2, 3p3. So you can very easily see that. Hopefully you can see that on the periodic table. Left to right, top to bottom. Here's manganese. Somebody read off manganese for me. What's this?
1s2, 2s2, 2p6,
2p6,
3s2,
3s2, 3p6, 4s2,
4s2,
3d5.
3d1, 2, 3, 4, 5. 3d5. That's manganese. Okay. It's not hard. It's probably going to take you a few examples doing it on your own in front of you before it really clicks. If it doesn't click, be sure to let me know, because it's not that complicated. It's not something you should sit at home struggling with. So, somebody want to come up, or just say it from your seat, electron configuration for aluminum. Somebody want to write it up here. Aluminum is here. Nope. Okay.
Right.
Thank you, Julie. Thank you. Yep. Thank you. 1s2, 2s2, 2p6, 3s2, 3p1. Okay. We're not gonna do all of these. Let's see what's the hardest one.
The last one.
Zinc, mercury. That mercury is too hard for us. That includes an F. The F's start here. Let's do cadmium. Somebody feel confident enough to do cadmium? No? Okay. What's this?
What?
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4d10. And so once like I said, once you get comfortable with this, you can say, well, where's cadmium? Cadmium is 4d10, so let me just fill in everything behind it. And just fill it all in. Okay. And then the last way is the shortest way. This is noble gas notation. Okay? This is like electron configuration, but it's assuming you know what you're doing. Okay? If, put it this way, I-75 is right here, right? I grew up in Michigan 5 minutes from I-75. Okay? If I get an I-75 and I head north on Michigan, I know I'm going to go through Atlanta, right? So if I am giving someone instructions and I'm telling them, get an I-75 and go, I don't have to give them instructions on how to get from Gainesville to Atlanta. They're on I-75. If I tell them, start at Atlanta and go from here, they can get to Atlanta on their own. That's basically what noble gas notation is telling you. So, if you have sodium and magnesium, the only thing that's different is sodium is 3s1, magnesium is 3s2. Everything that's back behind here is the same. So what we're going to do is we're going to say, we're going to start at neon. This is our starting point, 3s1. And then for magnesium, it's start at neon and then go 3s2. So you're going to save all of this stuff here. So iron, if we write out the electron configuration for iron, you get that. Argon is this. And so this here is the same as this here. So we're going to use argon as a reference point. We're going to say we're going to start at argon, and then we're going to do 4s2, 3d6. And so it becomes iron is argon. You put argon in brackets. It always has to be a noble gas. You can't start with something other than a noble gas. So it's argon, 4s2, 3d6. So for the short ones, it may not save you a lot of writing. But when you get long, and iron isn't even all that long. Iron's right here. Imagine doing tellurium or something. You're going to have a whole bunch. You don't have to write it up. If you're doing tellurium, you just start at krypton and then just do these here. It saves you a lot of work. Unfortunately, there will not be many chances that you get to choose which one you want to do. According to learning objectives, you need to be able to do all three, which means the question is probably going to tell you which one to do. So make sure you read the question. It's going to be asking you which one it wants you to do. Okay, we're going to take our break here. We'll start at 7:40 on that clock. Go ahead.
Katsu.
So what we're trying to do, we're trying to figure out electronic configuration. Electron configuration, going to normal gas with the ions. The electron configuration in the orbital diagram and the normal gas, we're dealing with different atoms. So aluminum is there, and it has 13 levels. So we're going to start here, and read across.
We're gonna cross the periods till we reach it.
Right. Left to right, top to bottom. So like that. So we've got 1s, 2s, P,
Okay. 1s, 2s. Why is it two? I know this is group P, why is it 2P? Focus. I know this, and we're in the second period, that's why it's 2.
Right.
Okay, and then
finish here, come down here, and then this one's 3s.
3S,
Just big number, 3s,
3P.
3p, and that's the 1 and the 3. That's 2, 3, 4, 5, 6 in the 3.
All right, now I'm getting a good understanding. Okay. All right. So, okay, I'm understanding.
Sure.
Yeah.
Which is, remember, S, D, P, be left to right, D, the number that's one behind. This is 3D, even though it's in 4. It's 4S, 3D, 4P, 5S, 4D, 5P.
So 4S, 3D, 4P. Okay, good.
I've seen it, yeah. At this point, what this does is it tells you going diagrams, right? So if you start here, you got 1S, 2S, 2P, 3S, 4S, 3D. So it's telling you the order. So the arrows are telling you the order that you fill them, but then these numbers, the rows here, are just the 1, the 2, 3, the 4, 5.
I was thinking was like one and two and then 3D and then
What it's doing is it's just trying to organize the boxes in a way that makes sense. With the 1s, the 2s, and the 3s, and the 4s.
the way
Right. So you fill the arrow. You fill that arrow with 1S, then that one is 2S, then that one starts at 2P, and then goes to 2S, and then 3P, 4S. Okay. If that makes sense, that's great. You won't have that on a clear the final map. Whereas,
I'll learn it. I have to learn it when I was in high school. So
because you will have this. So if you can do it based on this, you'll have this.
yeah, but I use the number for the other.
So do you want to,
It will
okay,
be my
get one of those yet? How about then we go get them?
No, I have copies.
What is that MVP section? We have 3 boxes. And then the S section.
So there are always No, there are 10. There's 10 arrows. Two per box. How many boxes?
What about going for, when they call about the 3D, they would want to go about 2 arrows.
You know, there should have. No, that's not.
That's all I have.
No.
Those 5 boxes.
There are 5 boxes. Cobalt has 1, 2, 3, 4, 5, 6. There's 7. 1, 2, 3, 4, 5, 6, 7. So you get 5 boxes. There's 1, 2, 3, 4, 5, and then you come back 6 and 7. So these two have 2. These 3 boxes.
I only have 1. All right. Okay. Yeah, it's pretty easy to get through, right? So it's not the click. Yeah, well, for a second, I was like, 'cause I need to do it. Actual second, the other one's going away. I just really need to go, like, more live. Is that the correct way to do it?
Left to right, top. Just like you're reading.
It was, cause I hadn't practiced the significant figures, so when I got my final answer, I read out to my friend, she's an organizer, so she helped me out, she told me the zeros, I said, figures, but the zeros aren't significant figures. Unless they're between.
Or to
not
the right.
zeros, or to the right of the decimal, right? Well, okay, for example, if it's like this, 0, 6, 5, 0, this 0 is this would correct. That's what it was.
Is that your question?
Yeah, that's. Thank you.
Now we're really going to start to talk about these valence electrons. I referred to them a couple times, and I said that the valence electrons are the ones on the outside. But now that we know about the orbitals, we can fill in where the electrons go. We can really talk about which electrons are on the outside. The valence electrons are the ones in the highest principal energy level. Looking up here, do you remember, how do you find the highest principal energy level? How do you find the principal energy level of something? It's just the period number, okay? So in our 1s2, that 1 was telling us the principal energy level of that s orbital. Okay? And so for a valence electron, it's just going to be the ones that are in the orbital that has the highest number. valence electrons are in the valence level. So if we go back a slide, we look at iron. Looking through this electron configuration, what is the highest principal energy level that you see?
4 is 2.
4. You see a 4. And so you just count how many electrons are in an orbital with a 4. 2. 2. 4 has 2. There are 2 electrons in the 4. Even though the D is past it, it's a 3. So it's not, it's a lower than a 4. So you just count the 4. So iron has 2 valence electrons. What about argon? What's the highest principal energy level you see there?
3,
3. How many valence electrons does argon have?
8,
8. 2 plus 6 is 8. Okay? So if you're doing it this way, you just find the number, find the highest number, and add up how many electrons are in an orbital with that number. It's actually going to be even easier once we get to the periodic table. You can do it visually again. How many valence electrons are in bromine? 7. The 4 is the higher number. So you have 4, 2, and 5. 2 plus 5 is 7. I look at the periodic table. And if looking at the periodic table is going to be the quick way to do it, that's going to be the way you're going to want to learn to do it. And it's easy. Start from the left and you count right. Ignore anything in the middle. You're just dealing with the S's and the P's. The D's will never count. Noble gases have 8. 8 is the most valence electrons you can have. You cannot have more than 8. And so, we'll come back to this. This one's the most confusing because it's 1. We'll start with 2 here. We'll start with period 2. Lithium has 1, 2, 3, 4, 5, 6, 7, 8. That's all you gotta do. We come down to period 4. We're going to ignore the D's. 1, 2, 3, 4, 5, 6, 7, 8. That's it.
That's valence electron.
That's valence electrons. That tells you how many are in the outer shell. Okay? And I said 1 is most difficult. 1's the most difficult because there is no P. So for hydrogen and helium, you can only have 2 valence electrons. Hydrogen has 1, helium has 2, and now you come back to 1 with lithium. Okay? So just start from the left, ignore your D's, and count. So, fluorine. Fluorine is here. How many does it have?
7,
7. Lithium? 1. Sodium?
1,
Carbon?
4,
4. 1, 2, 3, 4. Silicon?
4,
4. Lead?
4,
4. 1, 2, 3, 4. So if you're in a group together, you have the same number of valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. It's not hard. To be honest, I forgot this was in here. Those numbers don't work. So we'll just do it without the phone thing. How many does titanium 2 have? You know?
I guess a 4.
I thought
I thought you said these don't count.
They,
you said.
Would it be 3?
I guess
2.
4. I guess
Let's do
4.
show of hands. How many say 1? How many say 2? How many say 3? How many say 4? How many say 5? Does anybody say something higher than 4 or 5? Okay. It is 2. These don't count. 1, 2, and then all of these have 2.
Oh my goodness.
1, 2, 2, because you're just adding these. These don't count.
I'm gonna show, so would you count this bottom number right here then for all of them? So it's 2?
like that's 1, 2, 3, 4, 5, like that, because.
I honestly, I never looked at those.
Yeah, see the bottom numbers?
Yeah.
So I think that's how it's coming, see how all of those are too?
Yeah, they are.
Right.
I don't think those numbers are on the periodic table on your cheat sheet. No, those
I know,
numbers are
but
not.
that would be the balance still of
Yeah.
that.
So, everything in the middle here is 2. Don't try and count how many D's you
Oh my
have.
goodness. All the middle, all the D is 2.
All of them have 2. So, we can do these electron configurations and the orbital diagrams in the noble gas notation for ions also. And it does not have to be difficult, okay? Just think about how many electrons that ion is going to have. If it's an anion, if it's negative, that means it gained electrons. So figure out how many it has, fill up your orbitals. If it's a cation, if it was a metal, if it lost electrons, figure out how many it had, fill up your orbitals. And these are actually going to be easy, because remember, they always try to get to be a noble gas. And so you're always going to end with a full p orbital. Always. And so if we had fluoride ion, how many electrons does a fluorine atom normally have? None. How many does a fluoride ion have? 10. It gained 1 to become neon. So you have 1s2, 2s2, 3p6. What about the oxygen ion? It starts with 8 and it ends with
10.
It gains 2 to get to 10. So the electron configuration is the same for the electron, for the oxygen, and the fluorine. It's going to be the same for the nitrogen. Their electron configuration is neon. So it's not hard. So we're going to do sodium. Sodium started with how many? 11. And what happened to them?
It lost
It lost 1 to go back to neon. Because it's in the group 1, it's going to form a +1 charge, which means it lost 1. So it goes back to neon. So again, we have 1s2, 2s2, 2p6, and you're done. Because we lost that one. We fell back to neon. 1s2, 2s2, 2p6. You can do the same thing with your boxes and your arrows. If you wanted to write the noble gas notation for sodium ion, how would you do it? If you wanted to write the noble gas notation for the sodium atom, like we were doing before, how would you do it? You'd start at neon, and then you do 3s1 for the atom. Now we're doing the ion. So what's the noble gas notation for the sodium ion? Just any. It's just neon. Because for the atom, it was that. But when it became an ion, it lost that. So you can't really write noble gas notation for ions because it's just a noble gas. These Lewis symbols in a few weeks are going to get a lot more complicated. But what we're doing today is not complicated. All you have to do is figure out how many valence electrons an atom has and put that many dots around the symbol. Okay? And there's just a little bit, a little order that you have to do it in. So how many valence electrons does lithium? 1. And so I'm going to write lithium. I'm going to put a dot. That represents one valence electron. Okay? And then we go to beryllium. I put 2 dots. And you tend to put them opposite each other. Electrons don't like to be with each other. They're antisocial. So the second one is going to go opposite the first one. And then we'll do a third one. So now you got 3, 4, and now we start pairing. 5, 6, 7, and 8. Basically, however many valence electrons you have, that's how many dots you should have. And don't pair them until you have to. You should have 4 single electrons before you go to the 5 and the 6 and 7 and 8. Yeah.
Does it matter exactly where you pair them?
No, I'm not going to grade you based off of that. I always learn to do top, bottom, left, right, top, bottom, left, right. But I'm not going to hold you to that. Just when you do the second one, put it opposite the first one, and then don't pair until you have to. You know, they didn't. The way I do it, that second pair would be opposite that pair, but they didn't even bother doing that.
Isn't that how you like put a tire on? Like go like off? I'm serious. Like
That's-
the nut.
It makes sense. Yeah, that way you don't over tighten one side or the other.
I swear.
Now that's how you're going to remember how to do this.
You better back me up. So.
It is.
Questions? That's not hard. Okay. The last topic for today's lecture are the periodic properties that we talked about. We said if you go from left to right, there are certain changes that happen, and they're predictable. And there are a few that we're going to talk about. The first is reactivity. We have ionization energy, atomic radius, and atomic radius. We're going to talk about each one is going to have its own slide or two. So as you move down a group, things become more reactive. So this is lithium in water. It actually is reactive. And then sodium, potassium, rubidium, and cesium. Okay? Last semester, somebody asked me why francium wasn't on the end there. Turns out it's so reactive, francium can't exist in our normal atmosphere. So you can't put a chunk of it in water because you can't get it to begin with. But you can see it's getting more and more reactive as you go down. That is a trend. The lower you are on the periodic table, the more reactive you are. Then we have ionization energy. Ionization energy, to me, is a confusing term. Because we talked about some atoms like to form positive ions, some of them like to form negative ions. And when I hear the term ionization energy, what I think of is how much energy it takes to make an ion, regardless of whether it's positive or negative. In actuality, what it is how much energy it takes to make a positive ion. Even if you're an atom that wants to make a negative, the ionization energy is how much energy it takes to make you go positive. So that kind of helps us. If you are lithium, do you want to go positive or negative?
Negative.
Do metals form positive or negative ions? Positive. Metals form positive ions. So lithium wants to become positive. If it wants to become positive, I'm not going to have to pay it very much. I'm not going to have to give it very much energy to make it become positive. If I'm fluorine, do I want to become positive or negative? Negative. And so you're going to have to pay me a whole lot in order to go positive. Because I want to gain an electron, and you want me to lose an electron. You're going to have to give me a whole lot of energy for that. It's like trying to get a Bernie Sanders supporter to vote for Donald Trump. Or the other way around. You're going to have to pay them a lot, right? That's not what they want to do. And so, things on the right, things that want to become negative, are going to have high ionization energies. You're going to have to pay them a lot. Things on the left are going to have low. So if you're familiar and comfortable with energies, we're not in this class at this point. Basically what this is saying is you take magnesium and you break an electron off of it, you have to put in 738 kilojoules per mole of magnesium. And that probably makes no sense to you, that unit. Don't worry about it. We haven't talked about moles or even joules yet. Okay. What this is saying, things with low ionization energy, things over here are not holding on to their electrons very hard. And so it's very easy to grab them and steal them away. The ones on the right side, the non-metals, are holding on very tight. So you're going to have to pull really hard to get an electron off of it. And so the trend is this. We said the ones on the left don't mind becoming positive. They're going to have low energies. The ones on the right do mind. They're going to have high energies. So as you go from left to right, the ionization energy increases. But there's also a trend going from top to bottom. At the top is higher. At the bottom is lower. And the reasoning is this. If you have a positive proton in the middle, in the nucleus, and a negative electron out in the clouds, positive and negative, do they attract or repel? They attract. Positive and negative attract. Opposites attract. And so those have an attractive force between them. That's what holds that electron in place. That's why it doesn't just fly off in space. If we have this atom down at the bottom, we now have a lot more electrons. Our cloud is a lot bigger. And so that electron is further away from that positive charge that's holding it on. And so it's a lot easier to grab this electron and pluck it off. If that makes sense to you, you can use that reasoning to figure out this trend when you come across it on an exam. That's how I do it. If you don't, that doesn't make sense to you, or you don't want to try to make it make sense, or you just want to forget it when you move on to the next slide, you can either remember these trends, increases going that way, increases going that way, or the way I would suggest is figure out which corner, there are 4 corners, which one is the highest. And if you increase going up and increase going over, that corner is the highest. And if you can remember that that corner is the highest, because that's at the top, it must be higher at the top. Because that's on the right, it must be higher on the top. The type of question you would get here is what has the higher ionization energy? Nitrogen or oxygen? Oxygen. It's further to the right. Which has the higher ionization energy? Nitrogen or phosphorus?
Nitrogen.
Nitrogen. It's higher towards the top. And so you can either remember that trend. You can say it's higher at the top and nitrogen is higher than phosphorus. Or you can remember helium is the highest. So which one's closest to helium? That one's going to be the highest.
So that's helium's spot, right?
Yes.
That's okay. So where is that over there?
It's over there because what is the electron configuration for helium?
It's S.
It's an S.
So that's the only reason why
But-
that's there.
Right. It's an S, but it's over here in the P's.
Okay.
And so somebody wrote helium over there in the S's. So that's ionization energy. Which one has it higher? Magnesium, magnesium or calcium? Magnesium, because it's higher. Oxygen or fluorine? Fluorine, because it's further right. What about sulfur or fluorine?
Fluorine.
Fluorine. Fluorine is further right, and it is higher. So if I told you oxygen or chlorine, that's an impossible question. You don't have enough information to figure that out. Chlorine is further right, but oxygen is higher. You won't get a question like that. Okay? If they're on a different row and a different column, it's going to be like this, where they both point to the same answer.
It doesn't matter if fluorine has more valence electrons?
No. It having more valence electrons is why it is a higher ionization energy because it's to the right. But because it's further down, those valence electrons are further from the nucleus. So there's a weaker attractive force. And so it's a question of which one wins out. And I don't know, so I can't ask you to know. And the last one is atomic radius. Plural of radius is radii. Radius is the distance in the nucleus to the outside of the electron cloud. So diameter is all the way across the circle, radius is from the center out. So this is just basically telling us the size of an atom. What's bigger, what's the bigger atom? At the top or the bottom? We already talked about that, right? Which one is bigger, the top or the bottom? Bottom. Why?
Further from the nucleus.
Why are they further from the nucleus? More electrons. We say as you add more electrons, your cloud has to get bigger. And so your atom gets bigger and bigger. That one makes sense. That one's easy to remember. As you add electrons, your atom gets bigger. What seems a little counterintuitive is this one. What has more electrons? Lithium or boron? Boron. But actually lithium is bigger. That's because when you add them in the same row, you're adding them within a shell. And once you add that first one to that shell is there. Adding more electrons to that shell doesn't make it bigger. You're not adding shells. It only gets bigger when you add shells. But what happens is as you add those electrons, you increase the attractive force between the center, the nucleus, and the electrons. The more positives and negatives you have, the larger the attraction. So the larger the attraction, it wants to pull that cloud in a little bit. It makes sense if you understand it. If that doesn't make sense, you're going to have to memorize the trend. Okay? I know the concept, so I don't have to memorize the trend. You can memorize that it increases as you go from right to left, or it decreases as you go left to right. Or you can remember which corner is the highest. Which corner is the highest? Bottom left on this one. This one's bottom left. So francium. If you can remember francium is the highest, you'll be okay. Which one is closer to francium? Whichever one is closer to francium is bigger. It's opposite of helium for the ionization energy. That's top right, radius is bottom left. If you can remember those two, you've got to figure out which element you're being asked about is closest to that. Yeah?
Sorry, so lithium is higher.
Lithium is larger than boron. Yeah. Does that make sense? Or at least can make sense if you memorize it? So this is just sort of a graphical thing so you can see it. So you can see that as you go down, clearly it gets bigger, and then as you go left to right, it actually does get smaller, even though you're adding electrons. So magnesium or calcium, which one is bigger? Calcium. Oxygen or fluorine?
Oxygen.
Oxygen. Sulfur or fluorine? Sulfur. Good? Okay. So we are going to go over the multiple choice part of the homework, the quiz. Any questions on this before we change study? This quiz has a lot of math on it, so I hope you brought your calculator. If you didn't, you're going to share my little one. Okay? So because there's a lot of math, this quiz takes significantly longer than most other quizzes will this semester. So we want to start